Alright, so this is example 3 in Module 7. And this example is going to be a combination of the first two examples. We're going to use some of the stuff that we used in example 1 and example 2 here. So basically we have an electron that's traveling around sort of a track-shaped path. And first I just want to remark at how outstanding this figure that I've drawn here is. Considering I drew it by hand, and considering how poorly I draw things by hand, and how poor my handwriting is. This is really just a great looking figure. Alright, so again, we have an electron that's traveling around this path, and we are asked to determine how long it takes the electron to make one complete revolution. So let's start off by looking at the electron up here. It is traveling around counterclockwise. How long does it take the electron to travel around this path and return to its initial position? Now, if we knew how fast the electron was moving, it would be very simple. That time that it takes, which we might call the period, would be equal to the distance that it travels divided by the speed that it travels at. First, let's figure out what the distance traveled is. So there are two straight portions here. One through the top capacitor and one through the bottom capacitor. And each of those distances, those straight portions, is a length d. So this distance L is going to be 2 times d plus however far it travels on the two circular portions here. So these are two semicircles, the left and the right side. They're half circles. And the circumference of a circle is just pi times the diameter of the circle. So I have a half of a circle on the left. So pi times the diameter of the circle divided by 2 plus pi times the diameter of the circle divided by 2. That just gives me 2 plus pi times this parameter d. So that's the length that is traveled. And then we could calculate what the time is by taking this length. Oops, see what I mean? And dividing it by the velocity. So now we've got to figure out how fast the particle is traveling. There's two pieces of to the motion. There's the motion outside of the capacitors, where the electron is traveling in just a uniform magnetic field. That's why it undergoes circular motion. And then when it gets inside the capacitor, there's going to be an electric field that counters or cancels the magnetic force and causes it to travel along a straight line. So the uniform circular motion part is just like example 2, and the straight line motion through the capacitor is just like example 1. Let's look at the circular motion part. So this is going to be just like example 2. And if you remember from example 2, we basically got down to the point where we had a mv over r is equal to a magnitude of the charge times magnetic field strength. So if you don't remember this, go back and watch example 2. This absolute value around the charge is because we're dealing with magnitudes of acceleration and force, so we need to have the magnitude of the charge. So in this case, mass is the mass of the electron, so that's going to be an m subscript e. Velocity is unknown. That's what we want to try to figure out. R, which is the radius of the circle that the electron travels around, is going to be that diameter over 2. The absolute value of the charge is going to be the absolute value of negative elementary charge, which will just be the elementary charge. And the magnetic field is unknown. So we have one equation with two unknowns. That means we need another equation. At least one more equation to try to determine what these two unknowns are. And so for that, we're gonna consider what happens inside the capacitors. Let's look at the top capacitor. So the top capacitor is connected to an EMF, and the top side of the capacitor is connected to the positive side of the EMF. So this is going to be the positive side of the capacitor. This is going to be the negative side of the capacitor. And we know that there's going to be a uniform electric field inside the capacitor. I should draw the field lines equally spaced if it's uniform. And it's going to point from the positive plate to the negative plate. We know that the magnitude of this uniform electric field from the Module 4 could be calculated by taking the potential difference between the plates, which is the EMF potential difference, and dividing by the distance between the plates. And if we look at that figure, the distance between the plates is a little d. We also know that the reason that the electron travels along a straight line is because the electric force and the magnetic force cancel each other. So this is like example 1. Now the difference here is that we have a negative charge. The electric force is actually going to point up in the opposite direction of the of the electric field. And then the magnetic force must point down. Now we could use this to determine what direction the magnetic field was pointing, actually. So in this case, we know that the force has to point down, but it's a negative charge. So if we were to apply the right-hand rule, we would point our thumb in the direction of the velocity, which would be to the left here. And I'm looking at the top plate. Velocity vector points to the left. And then I would have to point my fingers in such a way that the back of my hand pointed down. All right, so your palm points in the direction of the force exerted on a positive charge. The back of your hand points in the direction of the force exerted on a negative charge. So I need to have the back of my hand pointing down while my thumb points to the left. And in order to do that, the fingers have to point out of the page. So the magnetic field must be pointing out of the page here. But we don't have to answer that question for this problem. What we do need to do, though, is try to relate the velocity and magnetic field strength together, and we can do that with this setup here. So remember from the first example that the magnitude of the electric field, the magnitude of the electric force has to be equal to the magnitude of the magnetic force. We know what the magnitude of the electric force is. It's the absolute value of the charge times the electric field strength. And we know what the magnitude of the magnetic force is. It's the absolute value of the charge times VB. So now we have electric field strength, which we can write in terms of the stuff that's known. That's the EMF voltage divided by the distance between the plates is equal to velocity of the electron times the magnetic field strength. So here's another equation that involves the velocity and the magnetic field. So we've got this equation with two unknowns, and then if we go up here, we have this equation with two unknowns. That means we can solve for both of those unknowns. Now what I want is the velocity, so I'm going to solve one for the magnetic field and then plug that into the other. So let me solve the bottom equation for magnetic field and then plug that into the top equation. So the magnetic field is going to be EMF over velocity times d. So that means if I now plug this into the top equation, left-hand side is the elementary charge times the magnetic field. I'm going to subscript this with an E because it's a constant. It's the electron's mass. Now I have one equation and one unknown, the velocity. So I just need to solve for the velocity. There we go. So I'm going to move the velocity to the right-hand side and move everything else to the left-hand side. Oops. That should be a little e. take the square root of that. And now I take that and plug it into the equation to calculate the period, which is just the length divided by this velocity. So that's going to be the 2 plus pi times d. And then I can just multiply by this this thing for the velocity inverted. So instead of dividing by the velocity, just invert it and multiply. So that'll be a 2med in the numerator. This stuff in the denominator, take the square root of it. So there is the time that it's going to take that electron to travel around the path once.